So now I request Dean Dr. Magendran, SCNRA Madurai, start the proceedings.
Soil where life begins, where food begins. There can be no life without soil and no soil without life. They have evolved together. And soil health is influenced by many factors, and one such factor is soil, fertilizers, and many uses. Green Revolution opened the gates for fertilizer application. Now it has been metamorphosed into smart fertilizer. In this session, our guest lecturer, Dr. Deepak Ranjan Biswas, Principal Scientist, Division of Soil Science and Agriculture Chemistry, Indian Council of Agriculture Research, Indian Agriculture Research Institute, New Delhi, President of International Society of Soil Science, will deliver a lecture on smart fertilizer. Now I would like to request Dr. N. Sendil, Dean of School of Postgraduate Studies, to welcome the gathering.
Thank you, the team SCNRA Madurai, for organizing the wonderful lecture by inviting one of the leading soil scientists working in Indian Agriculture Research Institute, New Delhi, and his talks today is on the smart fertilizers and how to improve the crops and applying various techniques on the nano-coated or the bio-inoculated material which enhance the soil nutrient use efficiency. Definitely will take you to the next level on the research. I think this lecture will definitely enlighten not only the soil scientists but also the people working on different sector of natural resource management. Really, I am happy that we welcome you, sir, for this today's evening lecture. This is one of the series of endowment lecture Tamil Nadu Agriculture University organizing. Not only the main campus, it also in the sub campus. And I thank Dr. Magendran for selecting the top speaker from the National Institute, and again all the college campuses students who are attending through online and also main campus. So, sir, for the information of the speaker, sir, this lecture we organizing every weekend Friday. The eminent speaker in the respective fields are attending delivering the lectures. And also these lectures are also archived in our YouTube and also your Microsoft team. And also we send the messages that been linked, and we already more than 1 month ahead in order to know the lectures timing, and also all the online platform as many of the audience are attending. So in this way, it is a unique kind of endowment lectures. We use both online platform and also physical platform. It's not only the students of soil science or the other related natural resource management, for other across all the discipline, the students of masters and PhDs are attending in order to know the cross-disciplinary knowledge and to have some to update on the cutting-edge technology in the area. So in this way, I really welcome you, sir, for this meeting. And also I thank SCNRA Madurai Dean Dr. Magendran for organizing this wonderful lecture. I hand over the mic to Dr. Balasubramaniam, NRM Director. He is with us. He will say a few words on this lecture.
Good afternoon, everyone. Good afternoon, Dr. Biswas. Really very happy to see you on the screen.
Thank you. Thank you.
Really, Dr. Biswas, we have a very close association for more than 2 decades in the Indian Society of Soil Science. It is a very renowned society in our country to respect to the soil health management. Dr. Biswas and his students at IRA has done a lot of work with related to the development of the fertilizers products from the various inputs. So his contribution to the soil science is immense, and he has many of his students got the Jawaharlal Nehru Award and also Indian Society of Soil Science Best Doctoral Award and Journal Award, all these things. So in these few words, I congratulate Dr. Biswas. He is actually having that Indian Science Congress Association in a national level. Indian Science Congress Association every year it will be held during January, wherein the Prime Minister of the country will inaugurate the Congress. He was the president of the Agriculture and Forestry section last year, and next year also is continue. So these few words, I wish him all things, and congratulate him for the Dr. Biswas lecture. Thank you.
Over to Dr. Magendran.
Thank you, sir, for extending your warm welcome to the gathering. Now I would like to request Dr. P.P. Mahendran, Dean, Agriculture College and Research Institute, Madurai, Vice President of International Society of Soil Science, to introduce the guest lecturer.
Most respected Dean SPGS, Director NRM, who have joined online. Our guest speaker, Dr. D.R. Biswas, Principal Scientist, IRA, New Delhi, Heads of Soil Science from TNA Coimbatore, Madurai, Kiligulam, Trichy, faculties and students who have joined online and offline. Good afternoon, everyone. This gives me an immense pleasure in introducing my close friend and very known eminent soil scientist, Dr. D.R. Biswas, to this August forum. I am extremely happy in introducing an eminent soil scientist at the national level, Dr. D.R. Biswas, Principal Scientist, IRA, New Delhi, who is going to deliver the endowment lecture on smart fertilizer for crop production and soil health. He did his BSc Agriculture in the year 1986 from BCKV, West Bengal. Subsequently, he completed his MSc Agri in Soil Science and Agricultural Chemistry in 1989 and PhD in the year 1992 from IRA, New Delhi. Later, he joined as the scientist in 1992 at IRA, New Delhi, and he was promoted to senior scientist in the year 2002. From 2009 onwards, he is working as a principal scientist at the Division of Soil Science and Agricultural Chemistry, IRA, New Delhi. He is the dedicated teacher associated in teaching for more than 30 years at Indian Agricultural Research Institute, New Delhi. Owing to his significant contribution in teaching and research, he got many awards and recognitions. He received IRA Best Teacher Award in 2015 for outstanding contribution and excellence in teaching in the discipline of soil science and agricultural chemistry. He is the recipient of World Phosphate Institute Fertilizer Association of India in the year 2012. He is the fellow in 3 well-reputed societies, namely Fellow of the National Academy of Agricultural Sciences, New Delhi, Fellow of the Indian Society of Soil Science, New Delhi, Fellow of the West Bengal Academy of Science and Technology, Kolkata. His contribution to overall growth and development of the Indian Society of Soil Science is highly significant because he served as treasurer of Indian Society of Soil Science from 2002 to 2012. Then he also acted as the secretary of Indian Society of Soil Science from 2013 to 2021. Currently, he is serving as the president of our prestigious ISSS. Further, he is serving as the president, Agriculture and Forestry Science section in the 108 session of the Indian Science Congress Association, Kolkata, during 2020. He is also extending his service as honorary editor of Everyman's Science, published by Indian Science Congress Association. He has published more than 263 research papers in national and international reputed journals, including book chapters, bulletins. So he has a total Google Scholar citations of 3,419 with the H index of 29, I index of 62. He has guided more than 35 MSc and PhD students. Most of them joined in agricultural research service under ICR. He traveled many foreign countries to share his scientific thought and knowledge. He visited Heavy Research Institute of Microbiology, Heavy Academy of Sciences, China in 2003. As Secretary of ISSS, he represented the Indian delegates in the Council meeting of International Union of Soil Sciences during 21st World Congress of Soil Science in 2018 at Rio de Janeiro, Brazil. As President of ISSS, he represented in 15th International Conference of the East and Southeast Asia Federation of Soil Science Societies as invited international speaker held during 2022 at Kuala Lumpur, Malaysia. So these are all the significant contribution made by our guest speaker. So thanks for the opportunity given.
Now, I invite the guest speaker, Dr. Deepak Ranjan Biswas, Principal Scientist, Division of Soil Science and Agriculture Chemistry, Indian Council of Agriculture Research, Indian Agriculture Research Institute, New Delhi, to deliver the lecture on smart fertilizer for crop production and soil health, a novel approach.
Thank you very much for giving me this opportunity to be here this afternoon. So first of all, I thank the Honorable Vice Chancellor, Dr. B. Geeta Lakshmi, and his team of Dr. N. Fentil. So thank you very much, sir. So in Agriculture College and Research Institute, Madurai, Dr. T.P. Mahendran, and he is the man behind these lectures. He is closely associated with me as a friend, and then he worked also in my lab during 2000 for 6 months, and since then I have this opportunity to have our friendships and interactions and so many things. Same is the case in Dr. P. Bala Subramaniam. Dr. Subramaniam, Dr. Bala. Dr. Bala is not hearing, so I used to call Dr. Bala Subramaniam, so director in having, and head of the department, Dr. Shiva, professor and head, Department of Soils and Environment, faculty of agriculture, and other faculties who joined online and offline in this university. So there are many colleges and they also joined the students in this endowment, PG endowment lectures. So thank you very much once again for inviting me. So I will be talking this smart fertilizer for crop productions, as already mentioned that students. I hope that is the students. Yes, that's correct. So he has introduced that our fertilizers. Use of fertilizers, that is very, very essential for crop production and to have to feed the increasing populations. And with the fertilizers, now we are going towards the new generation fertilizers. That new generation fertilizer is that smart fertilizers. So I'll be talking on that. And whatever that approach is there, what is the approach, and then how many research work we are conducting in our department as a scientist, and my students, they are working, as Dr. Balasubramanian already told you, that I am working through my students different type of development of fertilizers materials. So I will be discussing on that aspects. So these are the general aspects I will be introducing. That Indian agriculture, as you know, this our two-thirds populations, we depends on this agriculture, and about say 17.5% of the world's human population and 15% of livestock populations are on our soils, which is having only 2.4% of the total land mass of the earth. So you can see that there is no scope for increasing that your land, and we have only that arable land around 142 million hectares. So we cannot increase the land. Moreover, that agricultural lands are going for other purposes. So it is in fact decreasing. So we are having this used to have this agricultural production through this only that efficient management of the nutrients or fertilizers, so that it will give this lesser amount of fertilizers and more amount of your crop productions. So that is the main purpose of these lectures. And these are the major challenges you can see at present in increasing population and food insecurity, shrinking arable lands already. Even water is also becoming very, very less for agricultural purpose. It is using for other purposes. Land degradation and deterioration of soil health is another problem. Then our soil is depleting this soil organic carbon. That is the very, very important, or you can say heart of the soil. Soil organic carbon that is also deteriorating as because of that our country is your tropical country, and there you can say that lots of organic matter immediately that is decomposing and they are escaping as carbon dioxide. So soil organic carbon is lost because of this. Then multi-nutrient deficiency is another reasons. You can say that major challenges, imbalanced use of fertilizers. Farmers are using only that urea or nitrogenous fertilizers and ignoring particularly this potassium part. So, that is giving this imbalanced use of fertilizers. Negative soil nutrient balance and low fertilizer use efficiency. As I told that fertilizer use efficiency is very, very less. I will come later on how much is the fertilizer use efficiency respective nutrients. Then decline crop response ratio and stagnation in productivity, and moreover the climate change. You can see that very, very your climate change in terms of heavy rainfall, drought, or other things are increasing day by day. And you can say these are the deterioration of soil health. These are, you can say, as high as let's say 104.2 million hectares of arable lands are degraded in one form to others. And these are already there water degradation, wind erosions, then acidity, salt affected soil. So many data are available in that website of that ICR. So you can have this. So different types of constants, physical constants, chemical constants, multi-nutrient deficiencies, all are there. Salt affected soils. I am not going in details on this. So these are then now these fertilizers, as you initiated, that fertilizer ensures food security of the country. So we have to have these fertilizers. We cannot escape this. So many nowadays people are talking this natural farming or organic farmings, but to feed our populations, fertilizer is required. So otherwise, that crop productions will not be there. We require more than 350 million tons of food grain production presents, and it is increasing with the population. We require more amount of your food grain population. Now, if you see this fertilizer production consumption at present, this is as per this Fertilizer Association of India, API. They are actually publishing their statistics that fertilizer data in terms of production as well as consumption. You can see this production side only that nitrogenous and phosphatic fertilizer are produced in India, but not a single kg of potassic fertilizer is produced. And consumption also you can see that majority is at the nitrogen side. Although the total 29.8, but share you can see 19.44 and 2.83 is the potassium. And whole amount of potassium is actually coming from outside. As such, this either in the form of sulfate of potash or muriate of potash. Maximum is muriate of potash, that is KCl, and sulfate of potash, K2SO4. These are the two forms of potassic fertilizers. Now, if you have this projected food grain productions, we require by another say 2030, 350 million tons of food grain productions, and for that, the NPK demand will be 45 million tons, and NPK consumption hardly will be 35 million tons, and there will be gap of at least 10 to 12 billion tons of nutrients. This gap has to be maintained from other sources, or alternately, you have to develop this your some low-grade minerals which are available in India, like rock phosphate or potassic sources like your West mica or glauconite, that is the source of potassium you can use, or you have to prepare that novel fertilizers or next generation fertilizers to increase the fertilizer use efficiency or nutrient use efficiency. Now, if you see this, our present scenario in the soil fertility all over India, 95% of the soils are deficient in available nitrogen, and 51 and 40% are either low and medium in terms of available P. But the situation is still better in case of available K. That's why people are not applying and they are ignoring potassic fertilizer. But once every time you are mining the potassium from the soils. So potassium, say high soil also now becoming deficient. And all India coordinated research project on micro and secondary nutrients and elements, pollutant elements in soils and plants, they have given the data that out of this total sample analyzed, it was observed that 43.4% of the sample in terms of micronutrient zinc are deficient, whereas boron is also another important element, which is 20.6% found deficient. So these needs more attention. And if you see this progressive nutrient deficiencies, in the early 1950s, nitrogen was the only deficient nutrients, and that's why at that time application of nitrogen through urea, it was sufficient for getting good crop growth. But nowadays it is increasing day by day with the process of decades. You can see that you have initially nitrogen, phosphorus, then zinc, and now it is becoming so many elements. And next time again it will be another new nutrients which will actually will be deficient. So these multi-nutrient deficiencies are occurring because of that main reason, that exclusive focus on NPK fertilizers, then nutrient mining, limited or no use of organic manures, and removal of burning of organic residues. That is also another point which is actually becoming the nutrient deficient. And I told that initially that your declining crop response to fertilizer, these are also another reasons. If you see this in 1960, this response ratio, this is the how much grain productions per kg of NPK applications. You can see from 12.1 it is decreasing, and now it further decreased below this 4. And major reasons are so many. Out of that, this law of diminishing return, inadequate and imbalanced fertilizer use, nutrient mining and increasing multi-nutrient deficiencies, all are already discussed. Lack of varietal breakthrough, that is also another point. Then poor crop management and climate change. This climate change is another. So we have to this not only that fertilizer, smart fertilizer, but climate smart agriculture is also another thing which is very, very required. So all these things actually declining this your crop response. Now, if you see this, I will be concentrating my research mainly this phosphorus and potassium. So I will be talking that why this phosphorus is very, very important. These are your textbook knowledge. If you see that no phosphorus, no food. That is the slogan already given here. So here, phosphorus is the second most important, and potassium is the third most important nutrients. And phosphorus has no substitute, and phosphorus comes from rock phosphate. That is the mining product. That is mainly the apatite, and it is the 11th most abundant element. But if you see this availability of phosphorus, it is very, very less. Both in case of your acid soil or alkaline soil, in both sides, availability of phosphorus is very, very less because of that either your iron or your aluminum fixed phosphate in the acid soil, or calcium fixed phosphate in case of your neutral to alkaline soil. Similarly, potassic fertilizers, if you see this potassium also very, very abundant, 2.5% of the earth crust, and 7th most abundant element. Even then also you can say nowadays potassium is becoming deficient because we are ignoring the potassium fertilizers, we are not applying. And this demand of peak fertilizer is coming from that rock phosphate, and there are 150 different types of minerals are available on the earth, but only for fertilizer production. So rock phosphate having 30% of P2O5, that is important. This 30% P2O5 that is most important. But in the Indian rock phosphate, mostly less than 18% of P2O5s, unsuitable for commercial production of SSP or DAP productions. But this can be utilized by some other ways. So I will be talking on that, how this low-grade rock phosphate can be utilized through composting technology or by other procedures. Even Dr. Mahendran also worked this low-grade rock phosphate by using the partial acidulated rock phosphate. So these are the avenues for which can be utilized, because this phosphate is also actually becoming very, very, you can say, declining In world market also, that phosphate is reserve itself is declining. And one estimate, I will show later on, one estimate says that after another 100 years or 150 years, that whole quantity of that high grade rock phosphate also will be exhausting. Then what next? So we have to think that alternate sources. And in case of your demand of potassium fertilizers, this situation is very, very pathetic. You can see that the whole amount of your potassium fertilizer are imported in the form of either KCl or that is muriate of potash or sulfate of potash. But India is fortunate that we have some low-grade materials like mica. That mica contains actually this 8 to 10% of potassium. Actually, the waste material comes from that mica mines. This mica is usually used for this electrical insulator. And during the process of electrical, this mica sheet, cleaning is necessary. And in that process, 75% of the mica goes to waste. This waste mica can be utilized. These are the waste mica sample. And some amount of this low-grade materials like glauconite, that is also available in plenty, particularly in Madhya Pradesh. But the government is not allowing for mining. That is the problem. Otherwise, this material can be utilized as a source of potassium fertilizers. Now you can see this low-grade rock phosphate can be utilized through composting technology by using this crop residue like your rice straw. And this rice straw, that residue burning is very, very prominent in particularly in the northern India. So that is because of that burning, lots of your carbon is lost, and soil is biodiversity is also declining because of this. But we can utilize this crop residue, having this say 140 million tons of surplus residue out of this 500 to 550 million tons of crop residue generated per year. We can use this crop residue by using this some value-added products, and we can have a enriched compost. Normally, the compost problem is that NPK concentration is very, very less, and that's why it is a bulky nature, particularly phosphorus, 0.2% of P2O5. So we can improve this by using this value-added compost. So here is that technology. We can utilize this low-grade rock phosphate through this composting technology by preparation of this compost using this urea, some amount of rock phosphate and waste mica. And these are the compositions we prepared. And we have this one ICR project also we completed long back 2008. And it was published also in many journals, including Bioresource Technology and other. So here is that so we can prepare that 1,000 tons of materials by using this crop, different type of residue, 1,000 kg, and urea can be added at the initial stages because we can reduce the CN ratio so that its decomposition will be faster. So this is one avenue. Now I will be coming to the main theme of this smart fertilizer. Now, what is the problem of conventional fertilizer? If you say these conventional fertilizers, in terms of NPK or micronutrient, use efficiency is very, very low. You can see that nitrogen use efficiency is 30 to 50%. Your potash, phosphorus 15 to 20, hardly exceeds 20, then after good management practices. Then potassium use efficiency is 60 to 70, and micronutrient use efficiency is less than 2 to 5%. And what happens if this your use efficiencies go, then the excess amount of nutrients which is lost in the environment are going for this losses of environment in terms of the water bodies or in terms of your gaseous form in the form of ammonia. So environmental problem will be there. So overdose is very, very harmful. And then environmental pollution is there, heavy metal pollution, sometimes that rock phosphate, foreign rock phosphate, particularly heavy metals are there, particularly cadmium. That cadmium concentration may be increased. And then higher application frequency will be there. Sometimes that your soil acidification will be there. Excessive use of say nitrogenous fertilizer, your soil acidification will be there. So these are not non-synchronous. If the fertilizer should be synchronous, whatever the fertilizer released from the fertilizer granule, that will be taken by the plant. Then your use efficiency will be moved. So that is the purpose of your this smart fertilizer. Now here I will be coming So why this smart fertilizer is there? To increase the nutrient use efficiency, so that whatever amount you are applying, that is releasing nutrients slowly, and that is utilized by the plant. So that there will be less of quantities of nutrients which is going to be lost, either by leaching losses or going to be by elemental form, say denitrification, or sometimes that ammonia volatilizations. So all type of losses will be negative. So earlier that our the cultural practices, the nutrient placement, all those options are there. So we are following these management aspects. Now the novel fertilizer formulation of this, smart fertilizers we are coming. So now what is the smart fertilizers? If you see this smart fertilizer is a fertilizer which works intelligently, synchronizing the release of nutrients in tandem with crop demands. So it will release the right amount of nutrients at right time, which will be supplied immediately to the plant uptake, so that losses will be less. So that is the and ultimately the environmental problem, pollution problems, other things will be minimized. So here also comes that smart, like the smart person. The smart person is having very clean, orderly, well dressed, showing a quick intelligence and quick in action. Smart fertilizer also is smart. So a smart fertilizer, based on its name, are also those fertilizer having low or devoid of impurities, and that means clean. Then once according to requirement of the plant and very quick in action. So these are the important things. Then molecule of smart fertilizer is water insoluble. It is not fully water soluble. If it is water soluble, immediately it is going to be lost by leaching losses and other problems. And it is going to be eutrophication or other problems will be there. So here the design molecules that allow sustained release of nutrients, so that it will be in the soil for a longer period, and then it will supply the nutrient to the crop for a longer periods. That's why that nutrient efficiency will be more. And it will be that your fertilizer molecules like nutrient storehouse. So these are the smart fertilizers. Different types of smart fertilizers. You can have this novel fertilizer formulations or slow release, control release fertilizers, and the nano fertilizer from nanoscale fertilizer inputs, or sometimes these bioformulations, all are there. And these your smart fertilizer and novel fertilizer, they will reduce the volatilization losses and reduce the nutrient leaching both ways, and ultimately improving the soil quality, improve water holding capacity, improve nutrient uptake, and improve environmental quality, improve your productivity and health, and in this microbial health. So overall, your soil health will be improved by this. So this diagram is showing everything. Now, how this smart fertilizer will work? Basically, the smart fertilizer is the fertilizer granule, which is either coated with this polymer or micronutrient or nanonutrients. So different types of nutrients will be coated here. So some coating material or physical barrier will be given, so that the release will be less, and it will be in synchronization with the crop demand. Always it is with synchronization. That's why whatever quantity of nutrient released from the fertilizer granule, it is taken by the plant. So there is no chance of losses. So if you can reduce this, then you can have this high nutrient use efficiency and friendly and sustainable crop productions will be there. So all these are the, now if you see this world over these smart fertilizers, that smart fertilizer nowadays, although we are talking, but in India it's a very say recent one. We don't have much work on this, and very little amount of this smart fertilizer are used. Only the 5 countries, you can say the China, USA, Japan, and Western countries, they are actually the main users of this smart fertilizers. Yeah. And now, different type of smart fertilizer. I told that one of the smart fertilizer, most important one is this control release fertilizer. The control release fertilizer are those fertilizers that delay the nutrient release in or increase the availability of nutrient for an extended period. That's what I told initially, that it should supply nutrient for a longer period to the crop, so that it will keep throughout the crop demand. Crop growth, the nutrient whichever is released by the fertilizer granule will be utilized. Working principle is the restricted entry of water. That water once entered into the fertilizer granule, then only it is releasing. If it is not that, if you keep that urea as such in a pot, it will be remaining as such. When water is added or when applied in the soils, water is in contact, then actually it is going to release your fertilizer material. And then providing diffusion barrier against dissolved nutrients. If you give that barrier, one physical barrier, then also it will protect the release. And controlled release of nutrients and probably minimize the nutrient losses by synchronizing with plant diversity. These are the working principle of your this slow release or controlled release fertilizers. And the criteria of slow release fertilizers is that as per this European Standard Committee Task Force, they have given that this slow release fertilizer or controlled release fertilizer, it should have some criteria that nutrient release should not exceed 15% in 24 hours. Then nutrient release should not exceed 75% in 28 days. And there must be at least 75% of the nutrient release during the whole crop period, that is your 40 to 360 days. So these are the criteria that should follow by this fertilizer, any fertilizers. So they may be considered as slow release or controlled release fertilizer. This slow release and controlled release, there are almost similar things. Only thing that this is a slow release fertilizer is a slowly release material. You cannot control the release rate. That is microbial degradation is there, microbial decomposition is there. But these controlled release fertilizers are chemically degraded, so you can control the release there. So that is the difference. But both are actually used for similar purpose. And these are the this fertilizer material are there. Once the water moves inside, then nutrients dissolve, and then nutrients will come out. So this is the basic hypothesis of this your controlled release fertilizer. The benefits of this controlled release fertilizer is that direct benefit is the saving in huge quantities of fertilizers, supplying nutrients to crops for longer period, increase use efficiency, less environmental pollution. Additional benefits that improve germination rates, reduce salt concentration, reduce seed toxicity and leaf burning, and reduces hazardous emissions. So these are additional advantages of your controlled release fertilizer. Now, important nitrogenous slow release fertilizers are these are theoretical standard book. If you go through the standard book, already it is there. But if you see this used in India, very rarely we are using this. These are already more than say 40, 50 years back. This fertilizer started, but still we are not using in the. So the student can go through that digital book or any fertilizer books. These standard materials are available. And now recent advances is that you have this your different types of fertilizers, particularly pea fertilizers. If you see this, most of the pea fertilizer developed early in the mid-90s by this IFDC, that is the International Fertilizer Development Center at Muscle at in USA. They are the pioneer worker of this fertilizer technology. Most of the fertilizers developed by them at Tennessee Valley Authority in the USA. So nowadays, the research are concentrating on the development of new generation fertilizers, and some of the recent findings are the polymer coated water soluble fertilizers, rhizosphere controlled fertilizers, that is RCF fertilizer, organic complex superabsorbent superphosphate, then slow release pea fertilizer with superabsorbent property, and nanophosphate fertilizers. So these are the recent new generation fertilizers, and different types of polymers are also used. As in case of it earlier, that sulfur coated or other gypsum coated. Now, polymer coated controlled release fertilizers are nowadays are using, and different types of organic, inorganic encapsulations we are giving. Encapsulation is some physical barrier we are giving here, and then biodegradable polymer coated controlled release fertilizers also useful. And out of this biodegradable, that there may be either hydrogel type material or non-hydrogel type of materials. So hydrogel type of materials are more efficient. They can absorb more water in the soils. They can hold as high as 500 times of water based on their actual mass or volume of the materials. Now, it was another different this fertilizer or that nano fertilizer, different type of nano fertilizer nowadays. Your nano rock phosphate or their nano urea already it is in the market that is manufactured by IFCO. Although there are controversies there, how much nitrogen is applying still there. And this nano fertilizer basically the nanoparticles. Nanoparticles means 1 to 100 nanometers in one size. They can absorb on the clay lattice, thereby prevent fixation. While releasing into the soil solution, then can be utilized by the plants. So these are the basic theme or hypothesis of nanoparticles, how they can be utilized or absorbed or reduce the fixation. And different types of your micronutrients nowadays also, zinc nanofertilizers also available. So all these materials, even nano clay composites, these are Dr. S.C. Datta in IRA also work on that. My students also work some of these nano clay composites. So I'll be discussing things. And for students to know this nano fertilizer, nanotechnology, this comes with this field, very eminent scientists, they work on this. First, this nanoscience was established by Nobel laureate Richard Feynman. So he was the man, first he saw that he was having this idea of nanotechnology by delivering his famous talk that there's plenty of room at the bottom. So that is the first talk given by him, Richard. And then although he has not given that exact term nanotechnology, nanotechnology term was later on given by this Norio, and then it was popularized by another scientist, Eric Drexler. So these are the your you can go through that history and nanotechnology. We are using this nanometer scale. So that is also known as Feynman scale. That is nanometer. So this you can go through that literature. You will find lots of literature in nanotechnology. I'm not going in details on that aspect. Now I was telling that how this nano fertilizers or your coated fertilizer will work. These coated fertilizers, there are maybe different types of coating materials are given. One is your semi-permeable membrane, another one is perforated membrane, and solid impermeable membrane. So these are the here. This is the semi-permeable membrane. Means here semi-permeable membrane. So water is go inside. Once this water go inside, then the osmotic pressure will increase. Once the osmotic pressure is increased, then it will burst, and then the release of nutrients will be there, and that time plant will be taking the nutrient for themselves. The second category, that there will be perforated holes, and this through this perforated holes, that water will enter into the granule, and then slowly through this the whole granule will not burst, but through this hole the release will be there. So this type of perforated impermeable membranes are good. Another one is solid impermeable membrane. In this case, the solid physical barrier is given. But this solid physical barrier, you have to use some microbial microorganisms so that during the decomposition, they will degrade and ultimately it will be making some hole, and then water will go inside and slowly the release of nutrients will be there. So these are the mechanisms. And how this slow release fertilizer or control release fertilizer or your nano fertilizer can be prepared. So you have to take the granules first, then you have to spray that material or protein purpose slowly and decrystallization, and that this step will be followed, and finally you get that your fully coated fertilizers. And that fully coated fertilizer have the characteristics of this specific concentration, stability, solubility, time control release, enhanced targeted activity. All these characteristics must follow for a particular type of your materials. Then only, and these are already I told that nano fertilizers, they are also having advantages over conventional. So they can be more efficient also. Only thing that some biosafety has to be maintained. Otherwise, this material also have higher fertilizer use efficiency, reduce soil absorption, fixation, then reduce fertilizer nutrient losses, all other activities as in case of your plant control release fertilizer. So nano fertilizer also will be there. So here also this nano fertilizer, same thing, that coating material will be there. And then the water will go inside, and once water goes inside, then slowly it will increase the osmotic pressure, and solution of fertilizer material will come out, and slowly, and that will be taken by the plant. So all this you can see everywhere, the mechanism is almost same. Now we have some work done. Now I will go one by one. My research work at IRI with my students and published in very good journal. This is the soil and pH research. We have prepared different types of coated fertilizers by using your ammonia, that treated ammonia and phosphoric acid at 2:1 and 1:1, as well as we use this rock phosphate from Udaipur and sulfuric acid and phosphoric acid. So we prepare different product A, product A, product B, product C, different products. Then we coated with this this polyvinyl alcohol and liquid paraffin, these coating materials, and then at 2 rates, 2 and 3%, and then develop this material. And these are characterized by chemically as well as morphologically by using different same name and X-ray diffractions, FTIR, all these things. And finally, we have seen that all these coated products are better in controlling the release of P than commercial DAP in water. So by seeing this, you can have this product are very, very good. Even here, there's you see this 2:1 ammonia and phosphoric acid, phosphorus is more. And here also you can see this phosphorus, total phosphorus is more. So these two category of material, one is rock phosphate based and another is phosphoric acid or ammonia based materials we can prepare. And these we compare in the release rate in the different temperature and different moisture, and it was observed that by increasing the coating, so slowly it will reduce the P release. But we have to consider that we have to standardize the material, that which rate of coating it will be better. So on that basis, it was observed that 2% coating is sufficient. We should not go beyond 2%. Then if it is more coating, then slowly it will release drastically that P, which cannot supply the nutrient to the plant. Even out of these two type of your coating material, this polyvinyl alcohol is better than your liquid paraffin. And again, we have seen that release rate at higher temperature, the release rate obviously will be higher. So this way, we can say that product, we can compare the release rate with this standard material, that is standard DAP. And it was observed that all this product A, B, C, D, we can see their release rate is less. Means this material can supply nutrient in the soil for a longer period. So that's why the slow release property of all these materials. And when we have seen this your crop yield in terms of your wheat yield, it was observed that P recovery from this all this product also higher compared to your DAP. So result demonstration that the newly manufactured coated P fertilizer proved to be a significantly better with commercial DAP and increasing grain yield and P recovery. So this can be an option of this material. So these are the actually our paper published in the soil and business. So these are the your highlights of the your schematic theme. Your material is prepared, then coating is prepared, then it is applied in the soil, and how this imported material is releasing nutrients for plant. And then these are the hypotheses we have proposed, that we prepared two types of materials. One is rock phosphate based, another one is your ammonia based. So I am explaining here this rock phosphate when reacting with sulfuric acid, these are the reaction. So this is monocalcium phosphate as calcium sulfate, as in case of SSP production. In this case, this is the phosphoric acid. Here only monocalcium phosphate will be there. And now when this we are reacting with or coating with this liquid paraffin. So liquid paraffin, then it is a TBA coated controlled release phosphate fertilizers. This coated phosphate fertilizers, now the water will go inside and then it will be slowly coming out. Now you see this here, when applied this material in acidic soil, then what happens? This polyvinyl coated contour release rock phosphate fertilizers, then it will dissociate it in this form. This is the your polyvinyl part, and this is the hydrogen part coming out. Now, in case of acid soil, so here this acid soil, in mostly that phosphate will be fixed either by aluminum phosphate or iron phosphate, and then this part, this part will be reacting, and they will form a chelate, and ultimately this aluminum, this polyvinyl alcohol chelate will be there, and releasing this phosphate. This phosphate will be set free, and then that can be utilized by the plant. In case of alkaline soil, this here proton that will be reacting with this tricalcium phosphate and other phosphate present in the alkaline soil. Then acidification process will be there, and then this will form this your dicalcium phosphate and your monocalcium phosphate, and ultimately this phosphate will be released. That can be. So these are the hypotheses in our paper we published this way. And so here another paper also published in this Journal of Soil Science and Plant Nutrition. So this is synthesis of polyvinyl alcohol and liquid paraffin based control release nitrogen phosphorus fertilizers. So we are supplying this NP. In this case, we are earlier it was the rock phosphate based. Now this is the phosphoric acid and liquid ammonia based fertilizers, and same procedure with this polyvinyl alcohol and your liquid paraffin we use. And we have seen that very good results. And these are the overall hypotheses that your uncoated material we are using, then spraying with this polyvinyl alcohol, other things, and we are producing this LP coated or your this polyvinyl coated materials. And once it is applied in the soils, the water enters inside. Same hypothesis that then that your osmotic pressure will increase, and then slowly the release will be there, and that will be taken by the plants. So these are the now another ways we prepare, that is known as your other your materials. One is here we use three different procedures. In one form, we use this starch polyvinyl alcohols. So why this starch is used nowadays? We cannot use this acrylamide, which is actually used for coating purpose or other thing. In this case, biodegradable materials we have to use. So starch we have isolated from this your wheat or rice straw, and that can be used. And second procedure is that we can use this oil-coated material. This mustard oil and linseed oil, we can use at different ratios. These ratios, and we can prepare different material, final products. And that product again we have characterized as per the chemically as well as morphologically through the scanning electron microscope, then TEM, then X-ray diffraction and FTIR. All this we have seen, and in the first cases also we different products prepared. After this, your material starts polyvinyl, we added this ammonium persulfate and formaldehyde. All these materials have to be standardized, and then starts polyvinyl alcohol and bentonite. We use this bentonite as clay so that the material can be prepared in a base material. Otherwise, it cannot prepare as such material. So we have different types of 0% bentonite clay, 5%, 10%, 15%, 20%. All these materials are also clay. And third material here, acrylic acid, then acrylic amide, and starch polyvinyl alcohol all mixed together. And then we have this clay polyvinyl starch based super absorbent polymers type of materials. So this three categories of material we prepared and then evaluated through incubation experiments, then pot culture experiments, and we are going at present the field experiments. And these are some bases of clay polymeric starch polyvinyl blended capsulation material, or CPSB. In short, it is known as CPSB. And then we have seen that biodegradability by using different types of microorganisms, as far as ammonia and trichromatina viridii also, and added in the soils. And we have seen that by using this microorganism, whether that biodegradability is increasing or not. So we have seen that the material is very good. And so this material then we have characterized in terms of all this, this is the extent diffraction analysis, and then we have measured this density of porosity, and these are very, very important parameters for characterizing a slow release fertilizer or biodegradable materials. So effects of clay content, when clay content is increasing, its density is increasing, whereas porosity is decreasing. So this indicates that you cannot go for beyond a certain percentage of your bentonite clay. So if you add more, your solubility, it will be too much restricted, then it will not supply the nutrient release. And if you see this absorption in water and NaCl, 0.9% NaCl, that is a standard procedure for characterizations. With more bentonite content, again, that this is also decreasing. So that is the, and extra diffraction also shows that relative crystallinity index of clay polymer starts blended coating films increased with increasing that clay content. So we have to be optimum at around say 5 or 10%, not more than that. So we cannot go. And these are some FTI spectra. So all these are chemistry and aspects. This spectra, FTI spectra is done to see that whether any specific this group are present or not. So by seeing that specific group, in this case, say that waste stressing vibration peaks in all these materials, they will indicate that your hydrogen bonding is there or not, other things. So that is also a characteristics, morphological characteristics of a particular materials. So these are nowadays standard procedures. Then we have seen that first that release pattern in water medium in terms of both the release of nitrogen and phosphorus, and it was observed all these materials we first seen that water medium, and then the soil medium, and finally that crop. So this CPHP encapsulation DAP we prepared at different rates. These are the rates different and then applied. And it was observed that release of amounts of this nitrogen and phosphorus than uncoated DAPs. So release that first of all that our material is suitable for releasing less amount of N and P. That the purpose of our this product development. Then increase in bentonite content stabilizes the CPSB structure. That's what I have told, that this clay content is required to stabilize the material. Otherwise, if it is break, then it's that basic property of the slow release will deplete. So that's why some amount of clay has to be added. But we have to optimize this amount. And these we published this carbohydrate polymers that is also very high ranking mass rating, more than 15 rating mass rating. And these are the materials when we have seen that these are whether these materials are biodegradable or not. So by using this asparagillus aureus and trichoderma viridie, we have seen added in the soil, and then cumulative release of this carbon dioxide as measured through this your sodium hydroxide trap method, you can measure the carbon dioxide release. So that indicates the biodegradability of the materials. And we have seen when this asparagillus aureus is added, so they are more biodegradable. So they are very fast. So higher degradation was observed in asparagillus aureus compared to your trichoderma viridie. So these are another these are the highlights of the paper that synthesized biodegradable clay polymeric starch PTA blended materials for encapsulating films or fertilizer encapsulation, and relative crystallinity index polymer densities of SBS and increased with bentonite, and water absorption. All these characteristics also decreased with the increased bentonite content, and half-life that is given from that equation. So it gives that your biodegradability of the material by using this asparagillus aureus. So all these are now these are the oil-based material. Now oil-based material we have added this mustard oil and linseed at 75% and 25%, and then 50% and 50%, and 25%, 75%, and then 100% linseed. So this 1, 2, 3, 4 different combinations we prepared the material, and then the DAP is coated with this material, oil, and then we have seen we have characterized the materials and then seen that their release pattern, and so all these are the surface images of the materials after preparation, and subsequently we have same way we have seen their release pattern in water mediums, and in this case also you can see that they have oil type 1, oil type 2, different types material added different rates, 4% or 8% material added on the soil basis. The result revealed that oil 1 coated DAP formulation released lesser quantities of nitrogen and P than oil 2 coated material. Now you have to see again this oil 2 means these are the 75% mustard oil and 25%, and these are 50-50. So these mustard oil materials are better, but you cannot add more amount of mustard oil. Basic thing that we cannot use this edible oil. We have to think that some non-edible oils, so that is better. Otherwise, that since mustard oil is used, basically that edible oil, so we can use cooking purpose. So commercially, if it is a non-edible oil, that is better. So our purpose is on that aspect. But we have seen that by using this double boil linseed and mustard oil still, so we can have different types of slow release fertilizers. And we have seen that this hard category of materials also, these are scanning electron microscope. So we measure scanning electron microscope materials, and you can see that these are very, very fibrous materials. These fibrous materials means they can have a very good property, again with different types of amount of clay content. So here also we have observed this biodegradability materials, same procedure by measuring this cumulative carbon dioxide evolutions, and it was observed that the CPSS1, that is most important. So they are good in terms of their properties. So this is also another available P and available. Again, it was available cumulative carbon dioxide. Now this available P, and in two soils we measured this in septic soil as well as party soils. And these are some real data. Although this is a pot culture experiments, now we are going to measure, evaluate this material with yield experiments. So still these are in process. So this you can see this your CPSB, this type of material is compared that uncoated DAP, then CPSB, oil based, and CPSS. These three different categories of material we measured, and it was observed that CPSB is better than other two type of materials in terms of your nutrient recovery. Then another experiments we use this nano clay polymer composite fertilizers over conventional. So we use different type of NCPC, that is nano clay composite, polymer composite, and prepare by using different types of clay. It is clearolite, mica, and smectite. So this is NCPC 1, NCPC 2, NCPC 3, and then we applied different rates, and it was observed in the different soils, alkisol, insectisol, and vertisol, and mean cumulative nitrogen recovery from NCPC 3, that is your using a smectite, that is giving better results. So we are in process by using different type of materials in different soils, having which material is giving better results. So all these things, so if you see the use of slow release fertilizer made out by NCPC resulted in 38% of more nitrogen recovery and 62% of more P recovery by using this material. But this NCPC, here it is not biodegradable NCPC. This is by using acrylamide. So these materials we have to standardize these materials. Now another student, my student work here is solubilization of rock phosphate itself by using this organic acid nano clay polymer composite. So we use basic material, different types of rock phosphate, type rock phosphate, and another one is Purulia rock phosphate. We have isolated in a nano size form. And that nano size materials, we use this nano clay polymer composite and then prepare this NCPC loaded materials. as per this Liang and Liu and modified by Dr. S. C. Datta, then we also worked on this aspect. So loading of NCBC was done at 2% rate with ammonium oxalate and that is either. And then after loading with organic acid, the products are dried and ground to get oxalic acid loaded and citric acid loaded material. Then these material again characterized by different methods, by SLAM, and these are the 2-layer rock phosphate, rock phosphate. By using this scanning electron microscope, you can see that this is the original rock phosphate. Very, very inert material. You can see that structure. And when this NCPC we have added with organic acid, this is a very, very granular form, very, very fibrous material. It indicates that it somewhat that morphological changes occurring in that inside that granular rock phosphate. That's why its availability is good. So this is the message from here. Then we have seen that the release pattern also, that it was observed that the oxalic acid NCBC was found better than your citric acid. And these indigenous rock phosphate like Puplia and Udaipur are promising through this. So if we compare that DAP, and if you see the DAP is here, that release this. But oxalic acid release pattern is more. So this low grade rock phosphate also can be utilized by a modification of this organic acid loaded NCBC. So here also that your again that yield data. So we have seen that all this we use this albisol and insectisol that effect was more because this is a P basis we are using. So albisol that more fixation is there. Necessarily that impact was less. Then we have used some of potassic fertilizers. In potassic fertilizer, we use this waste mica as a source of raw materials. And basically, this waste mica, at present, this is not used as such in fertilizer material. Usually, I told that these are the materials used for insulating purpose. So, electrical insulator. And it is in sheets, like this type of sheet, one mica sheet. And after mining, this has to be cleaned to make a sheet. And during the process, about 75% of the material goes to waste. And that contains around 8 to 10% of potassium. So this potassium, how best we can utilize? For that, we have used this microbiological technique. Another one is composting. Earlier already told that composting also we can use. And during composting, lots of organic acids are generated. That organic acid helps in solubilization of both rock phosphate and this mica. Okay, so here also this microorganisms also actually they will release different types of organic acid. That organic acid helps in solubilization of this mica also. So here that mobilization of waste mica by potassium solubilizing bacteria. So we used this one of my students long back in the 2006. He worked on this and published this paper in Plant and Soil. And that was the first paper published in this potassium solubilizing bacteria in India. You will not get before that this potassium solubilizing bacteria. So here we use this potassium solubilizing bacteria. Basically, this is Bacillus mucilaginous materials. So here this is the Plant and Soil we published in 2009, and it has more than nearly 400 citations at present. So here we use this raw mica along with this Bacillus. When we have seen that without Bacillus and with Bacillus, that it significantly improved the your availability of potassium, and finally it will increase your yield of Sudan grass. So we use the Sudan grass as a test crop because the Sudan crop is a very, very exhaustive crop in terms of potassium loving crop. So that's why we have taken different cuttings during this 150 days, and we measured this. And both the uptake as well as your this potassium uptake and this is the yield uptake. So in both cases, wherever that solubilizing bacteria is used, then this also we have seen that if we add this along with this Bacillus another nitrogenous solubilizing or nitrogen fixing bacteria. So this nitrogen fixing bacteria we use here, so as a nitrogen fixer. So both by using, you can say the co-inoculation of potassium solubilizing and nitrogen fixing bacteria, there it will be impact will be more. So yield will be more in that case And you can see that here, this one, it is mica at the rate of 100 milligram kg of materials, along with your case fertilizer as well as nitrogen fixers. This nitrogen fixer is the azotopic curve we have used in this case. Then it was observed that then this same potassium source, that waste mica, we have added different types of isolated different microorganisms from Jharkhand, and then it was used. So since this mica is also available in plenty in Jharkhand area, particularly Giridih and Kodarma area, those mica mines are available in plenty. So he used that same source and some material soil we have collected and isolated that microorganism which is responsible for this. So this KSB1, that is basically Bacillus species, and another one is Pseudomonas species we have isolated, and then along with these two this bacteria, we have used some organic acid also. In the organic acid, again oxalic and citric acid in combination of this material, then we have seen that whether this water-soluble potassium as well as extrinsic potassium is increasing or not, we have seen. And it was observed and compared with this standard potassic fertilizer, that is mulate of potash. And it was observed that mulate of potash, although initially it is giving higher water-soluble potassium, but later on, after say 45 to 60 days, the other material is giving better results. It indicates that initially, although this material cannot supply sufficient amount of potassium, but later stages it can be utilized. So if we have a small quantity of water-soluble potassium at the initial stages, so that the crop at the initial supply will be met from that soluble potassium, that is mulate of potash, and the later stages this waste mica along with this potassium solubilizing bacteria will help. So all different combination you can see this they are very good in terms of water soluble K, extrinsic K also. And among these two solubilizers, your your KSB1 is was found that Bacillus was found better than that Pseudomonas. Then yield also we have seen that in Alkisol from Jharkhand, and it was also observed that see this mulate of potash compared to mica, it is higher in this case. But when this oxalic acid treated materials or treated materials are added, it is comparable. So it indicates that this material can be used as a source of supplying potassium. And this waste mica, which is otherwise not utilized as a source of potassium, can be utilized as an alternative source of materials. We have done some field experiments also. In that case, we use this 50% of supplying potassium to mica and 50% rock phosphate along with this KSB, PSB, and then 50% of the rock P and K are supplying this mulate of potassium. So by combining different ratios, we have seen that this material is giving better. So as I told that if we add initial stages that water soluble P and K, so subsequently the crop will take care and utilize this other material, alternative materials from here. So I can conclude that novel formulation like polymer coated 4-release fertilizer and organic acid loaded CPC would be an alternative to fertilizer to reduce the dependency on this water soluble fertilizer like DAP or mulate of potash. And so this can be an evident. So it is just started, and now we have to finalize, modify, and finally evaluate through the field experiment. Then only we have that it can be suited. And then biointervention of this waste mica with ASP also another way to utilize this potassium source. Now, before I conclude, the other thing we have to see this perspective of novel formulation very good. That is low down, and it will enhance the nutrient efficiency and nutrient fertilizer losses. But other thing we have to consider that novel fertilizer formulation have been shown to improve the crop yields and several materials as these are the already I have discussed that all materials, but it has to be standardized. And before the future research should continue to explore and evaluate the composition, manufacturing, process, and economic solution. These are the needs of the hour. And so we have to still continue at the refining and the rates and other things, and cost also. The cost, whether it is giving cost effective or not. So all these things, then only we can say that this smooth release or smart fertilizer will be very good in the future. And the constants of Nobel formulation is that the Nobel fertilizer formulation are designed to synchronize plant demand, but it really they do not due to many factors. Other factors, moisture content, temperature, and so many other things, the pH condition, bioavailability, so all these factors has to be considered in the field itself. Then only, like your biofertilizer. Biofertilizer is very good, but in field when it is applied, its efficiency is very less because of so many environmental problems. So in ideal condition, it is good. So controlled release fertilizers are becoming popular, but the coating is so far have not been environmental. So this coating rate also has to be standardized by preparing different type of products, then applying in the field, and different soil, different crops, all those things are needed. Then the material has to be biodegradable so that no residue should be left behind after application of the materials. So it has to be and cost effective. Then controlled release fertilizer needs proper management practices for their delivery system in synchronization of the crop. So delivery system also you have to properly apply the material. So all these things has to be considered. Then nano-based fertilizers or nano fertilizer also because biosafety. Because sometimes the nano size particles at that time of the application, if that powder material goes inside the users, so it is very, very harmful. So that biosafety has to be considered. And more about this India you can say that we are at the beginning of the smart fertilizers. And so Nobel fertilizer development is the need of the hour. So field experiments and future research. So next generation fertilizers, it will be there. So we have to what are the finding of this material. So thank you very much. So with this, I once again thank the organizer, particularly Dr. Mahendran and all other associated, Dr. Shiva and Dr. Andan, and all those who are associated in this program, including Dr. Senthil, Dean, School of Postgraduate Studies, and Director of Research, Dr. P. Balasubramanian. Thank you very much.
Thank you so much. With your detailed and informative lecture based on your outstanding work in this field, the knowledge gained will be helpful in carrying out research project in the future. Now, the section is open for discussion.
Other than that oil and clay, what are the other possible sources for coating, biodegradable coating?
The starch now, this starts even wheat. We are collecting the starch materials from wheat. That is even straw material. Straw after grinding properly, we can rice straw.
Most of the coating CMC they are using.
Huh?
CMC, cellulose.
Cellulosic, yes.
But
That is good. This should be biodegradable. Other, if it is not biodegradable, then it will remain as such that the whole, it will not release that material also. In soil, microorganisms are there. You know that large number of microorganisms, so they will work once it is applied. That's why it is biodegradable. That carbon dioxide evaluation is done for that purpose, to see this biodegradability of material.
so you have tried 3 different kind of biodegradable material. One is oil, mustard oil, linseed oil. Then you have used citric acid and other oxalic acids,
Organic acid.
organic acids. Then clay. So among the 3, which one is giving more
The clay is the
playable
base material for holding the material.
material? Okay.
Not
Coating material. Okay.
coating
So
is done by this other polyvinyl alcohol or liquid paraffin. So these are coating material. Same way that your starch material, so this is coating material. Earlier that you have had this sulfur coated material, lac coated material. Those sulfur coated, lac coated materials, even gypsum coated material, urea,
Yes.
particularly nitrogenous fertilizer. That is people long back. Still, it is not. We are not using these materials. Moreover, the cost of the product is also low. At the time of preparation itself, you have to coat very finely. If it is, it should not be irregular. If thin coating should be there, proper coating. So manufacturing itself, the cost is extra compared to your normal use. But there is avenue. Students, even next generation.
Yes, yes.
So
Yeah.
here also, you are smart also. Most of the students nowadays is smart. Already I have seen that definition of smart.
Smart.
So everybody is smart.
Smart.
India is number one in the mica production. West mica is having that potassium is very good, but 8% of the potassium is there. How much we can use?
8% is total potassium. This total potassium is insoluble material. I am telling. Now this insolubility can be improved by either microorganisms or through composting technology. That
Bacteria, by the bacteria.
bacteria, definitely bacteria. That is that potassium solubilized in bacteria.
How much we can use out of 8%?
Out of
Exactly.
only 5 to 10% for one crop, not more than that.
Mainly the Jharkhand.
Jharkhand area, that total
is having
area.
the best mica.
Wherever that mica, even in south also some micas, Andhra Pradesh also some mica. In glauconite are available in plenty in Madhya Pradesh. But government, they are not allowing that mining at present. If they allow for mining in the API or in the ICR level, lots of discussion I have heard that this glauconite should be utilized properly. Last 5 years I am hearing. I have tried also, but I could not collect that glauconite. That contains around 7 to 8% of potassium. This is known as green sand. This green sand is having, see, once you are getting that finished product from outside, ready-made product, so it will continue. Once government is closing that your road, automatically we have to see that alternate way.
Mine workers are also affected by this mica.
Yeah.
Most of the mine workers.
So that is actually government policy. That, but it has good opportunity. Similarly, low-grade rock phosphate, that is also not commercially used by the manufacturing. Manufacturing people, they normally import that high-grade rock phosphate, 30% P2O5, and sulfuric acid also, or sulfur, elemental sulfur. Then importing here and then preparing this sulfuric acid, and after sulfuric acid, reacting with rock phosphate, then preparing phosphoric acid, and from that phosphoric acid, by reacting with ammonia, they are producing ammonia, TAP or ammonia. Same way, when rock phosphate is reacting sulfuric acid, directly it is producing SSP, single superphosphate. That is the manufacturing process. So whole quantity we are importing and manufacturing in case of phosphorus. But in case of potassium, we are as such raw material, when finished product we are importing. For that purpose, the cost of potassic fertilizer in India is low. And since in soil, that potassic fertilizer is somewhat higher, medium to higher, people are thinking that no need potassium application. There are other sources also nowadays, that crop residue and other material is also. Two of my students now working on this native phosphorus buildup. How this native phosphorus can be utilized by utilizing some silicon material. By using that is another I have not covered here. So that is also native phosphorus can be, same way potassium also can be mobilized. And if we don't have any ready-made materials, then only we will do. As long as we are getting this material, but you have heard already that farmers are not getting DAP or at the right time, or even MOP at right time. So there was human cry last year also.
Here also we have shortage of DAP, sir.
So
So now we are recommending SSP.
basically, that basic research is required. So we have done small scale in laboratory and particularly pot culture. Now, in large scale, some manufacturing company in collaboration with this can be modified, and then for field experiment.
Very good afternoon, Dr. Biswas. I'm very happy you have made a wonderful and comprehensive presentation for this, particularly for the benefit of students community with respect to the various fertilizer products, especially the potassium and phosphorus. For the benefit of the farming community, you made a very production at the very low cost production technology you have developed. Really, it will be, if it is goes to the large scale production, really it will be give wonder to the farmers. So farmers' cost of inputs towards the fertilizer will be reduced drastically. Thereby, the farmers' income will be enhanced. So I want to add some of the points with this with respect to nano urea. So the nano urea, of course, the efficiency is more, but the quantum of we apply is very less. But such things, it is under debatable. So TNIU is also taken up the studies with using the N15 urea in comparison with the normal urea and nano foliar spray urea. So that such research is being done in TNIU, and TNIU is also taken up some of the basic aspects of the safety, biosafety of the nano fertilizers. So our head of the department, nanotechnology, that is Center for Agriculture Nanotechnology, Dr. K. Subramaniam, is in one of the member in the parliamentary committee in the biosafety aspects. So really good presentation, Dr. Biswas. Thank you very much. I hand over the mic to the Dean SPGS.
Thank you very much.
So thank you, Dr. Biswas, giving a very wonderful lecture today. We all benefited. So my one question is, the biosafety regulations are not, what is the stage of the biosafety on the nanofertilizers or nano material in the soil? If you have any update, please, I want to know.
Sir, I don't have this update, but still it is in process only. And already Dr. Balasubramanian is telling that Dr. Subramanian, what is his name? Subramanian. So he is working on that nano fertilizer. Actually, we are not as such working on this nano fertilizer directly. We are basically preparing this coated material type. This coated material somewhat biosafety is better. But as such, if you say measurable point, we have not done in field condition or other ways also. I also don't know how much is the present scenario in parliament or other. Once it is prepared, then this Fertilizer Association of India, they are the authorizing agency. They can have this type of material before popularizing in India. So they can give that exact biosafety points. What should be the biosafety?
Good evening, Dr. Biswas. This is Shanti Prosan, Head Soils from Coimbatore.
Madam, good afternoon.
Good afternoon.
Good evening already.
Actually, it is good evening. Actually, in fact, during my visit to IIRI with you on 9th, I think I have visited your students' pot experiment also with that oil-coated formulation. Really, that was, really
So
the treatment.
you visited that.
Really that treatment difference was very significant. So I think a part of the thing also you presented today, I hope. And here also, many of our PG and PhD students are working on this type of coated fertilizers to meet with the current need of the country, wherein especially the cost of the potassic fertilizer is very huge. And today also there is a query from farmer how to manage the potassium fertilization for crops. So in that angle, it is actually, your lecture was really excellent and an overall coverage of the smart delivery of fertilizers. So this is what I would like to convey to the forum.
Thank you, madam.
Sir, I have one query. In Indian condition, 70% of area is rain condition and 45% of grain production also comes from that. Is there any peculiar smart fertilizer for inferred area?
Not that way. It is. We have to work on that aspect. There is no specifically that rain fed or this irrigated. So even how much quantity at present it is used in India, that data is also not available. This is only that at the development stage that this material can be prepared this way. So it is not commercialized product. It's still in that process. Not exactly the manufacturing unit. No, not a single manufacturing unit. Smart fertilizer, your nano fertilizer, IFCO nano urea. That IFCO nano urea at present it is using. There are lots of controversy. Why group? That how that that 120 kg of nitrogen per hectare is actually supplying by only one bottle of urea. So there is a question mark on that aspect. So in IRA, this nano urea, lots of the field experiments are going on. They are applying 75% of the normal NPK. Additionally, they are giving that 1 or 3 spray. That nano spray. So if you give that thing, then only it is comparable with that 100% of urea, normal urea. So that way, still that data is not available. And it is not specific that whether it is a rain-fed or irrigated condition or it is in the summer or winter. That way also not classified. So this data, once it is popularized, and then these data are available from this Fertilizer Association of India. I have given that one only the total list. So in Fertilizer Association, they published this one book that is known as Fertilizer Statistics. So every year they are updating. That is the reliable source. That fertilizer statistics. So if you go through the fertilizer statistics, that how much quantity of fertilizer used in rain-fed condition, in irrigated condition, or in whether it is in Kharif or winter, monthly also they are publishing this data. So you can go through that fertilizer statistics. Every time it is updated. Every year they published one and updating this. Based on this update again, based on that how much fertilizer is actually sold in that particular district or particular area. On that basis, they collect the data. Once your manufacturing is there, now it is distributed in different villages or different districts. So they collect the data from the dealer. So on that basis, they are. So this is the process. Since it is in initial stages, we don't have that type of data. So that already we have measured that this coating material in 2 conditions. One is your moisture content, 1/3 moisture content, and then field condition moisture, and another one is your 1/3 field condition moisture. So that it is resembled that in the case of irrigated and your that non-irrigated condition. On that basis, as well as 2 temperature also, 20 degrees centigrade and another one is 35 degrees, so that it is resembled to the winter and summer. So this way also we have seen the temperature or moisture variation.
So myself, R. M.S. Kumar, 3rd PhD scholar, Department of Soil Science and Agriculture Chemistry. Sir, you told control lease fertilizers, slow release fertilizers, coated fertilizers. Sir, how long it will present in the soil? How we know reapplication? How we find out that, sir?
In soil?
How long it will present in soil, sir? Once
So that depends on the type of materials. Type of materials. Ideally, I have given that specifically that European countries, the Union, they have given that timings. It's 15% within say. I have already. Yeah. So this one you can see that the European Standardization Committee Task Force, they have given that slow release fertilizer or control release fertilizer. Their criteria 25 degrees centigrade temperature. So nutrient release should not exceed 15% within 1 day, and nutrient release should not exceed 75% 28 days, and 75% nutrient release should be within this period. So your material has to be prepared in such a way that they should follow this criteria. Then only you can say that you are. And actual measurement you have to monitor and then see in different conditions, same material, If the other condition, your moisture condition, your soil temperature, pH, all other thing will influence. So ideally, this will not actually maintain. So actual measurement, you have to do the research. Then only you can say that in this soil, this particular material will be available for such and such period. Exactly, I cannot tell in different particular soil. Ideal, this is the ideal condition. If all other factors are constant, then only this can be maintained.
Okay.
So this committee has given some, based on their research, they have already given this criteria. But actually, it will follow that what is the other factors, soil factors, your crop factors, your irrigation or rainfall. So many other factors will be there.
Okay.
So in field condition, every time, that's why we always depend on climate. So climate smart fertilizer, everything will be climate smart, fertilizer smart, everybody will be smart, then only that precision agriculture we have to. But in reality, it is very difficult.
So this is
Thank you.
for all type. So this is for all type of soil, or based on soil type, the amount of application appropriate amount will vary, sir.
Yeah, definitely, it will vary depending on the crop, soil. So site specific, I think you have heard this customized fertilizer or site specific nutrient management. So for that also you require a particular brand, customized fertilizer based on your soil type, based on your crop, based on your region, based on the season. So all this customized fertilizer is also one type of this your smart fertilizer.
Myself is Kogila. Sir, in terms of polymers, the surface behavior like hydrophobic or hydrophilic, how does it work in the stability in soil? Sir?
No. These two things are there.
Hydrophilic and hydrophobic.
Hydrophobic and hydrophilic. These two things means that they love water and they actually hate the water. So water molecule, actually this fertilizer material, whenever you will apply in the soil, that water should go inside the fertilizer granule, then only the release of nutrient will be there. If no water in the soil, dry soil, ideally it should remain as such, the fertilizer material. There should not be any decomposition and anything. So definitely in soil, due to moisture, some moisture will be there. If it is hydrophilic, so automatically that means that material is very water loving. Immediately water will go inside and its solubility will be very, very fast. That type of material is not ideal. Okay. But in if it is totally hydrophobic also, that is also not good. That is also not good. Ideally, it is somewhat good, but at the end, you have to supply the nutrient to the plant. The release should be optimum. So moisture content should be optimum in your soil, so that release pattern also will be for longer duration. That's why this hydrogel type materials, that is more efficient. If it is hydrogel type materials, they can absorb moisture. They will not. They will remain the fertilizer granule in a say small volume, so they can absorb 500 times of your water based on their own mass or volume or surface. Okay. So they can absorb.
I would request Dr. Shiva, Professor and Department of Soil Science and Agriculture Chemistry, Agriculture College and Research Institute, Madurai, to deliver the formal vote of thanks.
Good evening, everybody. Respected Vice Chancellor, the Dean SPGS, Director NRM, Dean AC Dare Madurai, Deans and Directors of Colleges and Directorates, Professor and Head, AC Dare Coimbatore, Trichy, Pilikula, and Professor and Heads of other departments. It is a great honor for us to join with Dean SPGS in hosting this endowment lecture. I am glad to be standing here to join on behalf of our department to express my vote of thanks. At the outset, I sincerely thank our Vice Chancellor for being a catalyst and stimulating us in all our activities to do the best. Our sincere gratitude to Dean SPGS, who is instrumental in designing all the endowment lecture series for the benefit of PG students and PhD students. I thank our Dean, ACN Direct Madurai, who always was a support and guiding us. Our chief guest is here only because of our Dean. Fortunately, he is a good friend of our team. And so, sir, I thank you very much for guiding us from the beginning to organize this lecture. Special thanks to our chief guest, Dr. Deepak Ranjan Biswas, Principal Scientist, IRA New Delhi, for accepting our invitation and to be with us here today. He has spared us valuable time traveling all the way from New Delhi. So it is a very great opportunity for us to learn from your expertise and hear your experiences. So today's lecture was very informative and enlightening. You have covered from all the basics to the advanced aspects, starting right from the need of fertilizer to different types of smart fertilizers and its response. Definitely, it would have been motivating and encouraging to our students. You have also shown a new path for our future research. Thank you very much, sir, for your enlightening lecture. And I thank all the scientists and students who are present online and offline, finding time to be here for hearing the lecture of an eminent soil scientist and make this event happen successfully. I thank the Professor Education, Dean SPGS, and all this team who have supported us in organizing this lecture. Finally, I'd be failing in my duty if I don't thank my staff and students of our department. My deep sense of appreciation to all my beloved students and staff who have made this day possible. And I thank Professor and Head Economics for making good arrangements, and also this team for making this hall and with all facilities. Thank you, one and all.